Okay, thank you, Nidhi, and thank you, everybody. Welcome to this 10th lecture in this series. Today, we'll talk about intra-seasonal variability of Indian monsoon. Why do we talk about Indian intra-seasonal variability? I think intra-seasonal variability. So far, I have talked about the monsoon climate, the seasonal mean and its interannual variability. But there is another variability of monsoon which is as important. That is the intra-seasonal variability, and that intra-seasonal variability actually contributes significantly to the seasonal mean and its interannual variability, and therefore we must understand this. And but for a long time, actually we thought that we did not know much about this intra-seasonal variability until about early 70s, when what is known as MGO today was discovered. We always thought that the time scales from about 1 day to about 10 days to about 100 days, this all is weather, these day-to-day fluctuations. And then we have this climate, seasonal mean and longer variability. Of course, that seasonal climate has a lot of other variability, like annual cycle, the year-to-year variability, interannual variability, like monsoon interannual variability. Then like ENSO is an example of interannual variability. Then there are multi-decadal variability of climate, that like in monsoon has a multi-decadal variability, Atlantic has a multi-decadal variability, then the PDO, Pacific Decadal Oscillation. So these are examples of multi-decadal variability. Then there are a whole bunch of centennial variations of climate. Then of course there are also suborbital millennial scale variability like Dunstad-Osgood oscillations. Then there are of course what is called orbital variations of climate in thousands of years, like 20,000 year cycle, 40,000 year cycle, 100,000 year cycle. These are related to the orbital variations of this sun of the solar system. And then there are of course tectonic variability, which are in millions of years, million years or more than several million years, because of the change of the landforms due to tectonic activity that changes the climate, but that is in a very, very slow time scale. So, but we thought that weather encompasses this whole range from 1 day to about 100 days. But we realized by about the early 70s that there is intra-seasonal variability within this 10-day to about 100 days time scale. There are variability which are distinctly different from the weather variability, which is about 1 to 10 day time scales. These are like low pressure systems, depressions, easterly waves that have a local, they're more like a local phenomenon and much smaller scales, but their dynamics is different. On the other hand, the intra-seasonal oscillations are much larger scale, almost global kind of phenomenon, and that they have a very different mechanism. So they are different entities, and therefore we have to understand them separately. And because they connect both weather and the climate, seasonal mean and their internal variability, these intra-seasonal oscillations act like a bridge between weather and climate, and that is what we did not realize before, but now we realize, and this has become a big field now, the intra-seasonal variability, and this has and we need to understand them, and also we need to predict them, these intra-seasonal variability, and that is what has come up to be a area of research called subseasonal to seasonal variations and seasonal prediction, subseasonal to seasonal prediction, subseasonal to seasonal variation. So this is the area where we are going to talk about today, and this region of intra-seasonal variability constitutes some of the major players are like Madden-Julian oscillations, or MGO. Then there is in the summer season we have the monsoon intra-seasonal oscillations, and we have the quasi-biweekly oscillations or quasi-biweekly mode. So these are the major players in this in the tropics over these time scales. And today, what I'm going to do I'm not going to talk about MGO very much, because that will take a much longer time. we'll concentrate which is related to the summer intra-seasonal oscillation. Those are the ones that are related to the Indian monsoon. And I will basically talk about the monsoon intra-seasonal oscillation. So this is within this time scale of about 10 to 100 days. In this time scale, there are two major oscillations that are known, which is one is in the time scale of about 30 to 60 days, and another is in the time scale of about 10 to 20 days. And these two are the major players in the related to the monsoon, and I'll talk about that today. And that are important because they modulate the weather phenomena like low depressions and tropical cyclones in one end, and also contribute to the seasonal mean and this year-to-year variation on the other end. Therefore, they are very, very important part of a monsoon system. And that is why we need to sort of understand. So what I'm going to do is just describe what we know about them so far. So it is, of course, a part of this. I have been talking about the Indian monsoon system as the seasonal migration of the ITCZ, and this is the whole intra-seasonal oscillations are a part of this the ITCZ system. And this, of course, gives rise to our seasonal cycle of the rainfall in the monsoon region. And the seasonal, the annual cycle of the rainfall over India is large rain during the summer season, but this large rain is not steady. This is a kind of climatological picture, like expected value over the monsoon season. But on a day-to-day basis, this annual cycle, it is shown here for 2 years over central India. If you look at a daily rainfall, these rainfalls have a lot of variations, and the variations have episodic behavior. They are not neither chaotic or not completely chaotic or very smooth. They're not steady. And you see that in this particular year, these are sometimes they're below normal. This green line is the kind of long-term climatology, daily climatology, and there is above normal period of above normal rainfall, then a period of below normal rainfall, and period of above normal, and they kind of fluctuated continuously. And these oscillations, in fact, this particular year, if you count during the 4-month period, there are something like 8 episodes, such episodes, which kind of makes it about a period of about 2 weeks. On the other hand, some other years, there you will see there are about 3 episodes within this 4-month season, making it about a 40-day period. So these oscillations are there within the monsoon system, and they are very integral part of our Indian monsoon system. And we need to understand what produces these, what drives them, can we predict them, and what is the mechanism behind the scale selection, why there is this 10 to 20 day mode has more energy, 30 to 60 day has more energy, why the other modes don't have energy in between. So this is Indian meteorologists have known this for a long time, actually, starting from Ramamurti and later I'll mention a couple of others later. But we knew this about this episodic behavior, and episodic behavior of the rainfall were known as active and break spells of rainfall. Sometimes the monsoon is active, and then there are periods monsoon takes a break, and this is a below normal period, and there is an above normal period. So these are called a break period and the active period. So people meteorologists knew this for a long time, but we did not know for a long time what are their spatiotemporal sort of exact characteristics, what are their propagation characteristics, and what is the spatial structure. That was not known for a long time until about late 70s. When I started the satellite picture and the analysis became available, then we started learning the kind of large-scale structure associated with these oscillations. And these have a very interesting sort of, you can see that there are a lot of variation, year-to-year variations. Sometimes there is a long break spells, and so this particular year, there's a big long break, and there are not many active spells. So therefore, this more frequent and longer break spells give rise to a seasonal mean, which becomes less than normal. So this was a drought year. And similarly, this was also a drought year. There are longer break spells. There are active spells, but not this was not a very bad drought year. On the other hand, you look at this year, there are very few break spells, and there is a lot of active spells, but active spells are not like very long. Active spells are also some broken up, but still you can see that this is a big active spell. But it is not like break spells. Break spells tend to become rather smooth and long. And on the other hand, active spells are always have fluctuations within them. But still, you can distinguish these spells, the active spells and the break spells clearly. And now we are beginning to understand them much better. So, in order to try to understand what are the kind of the temporal characteristics of this, Krishnamurti and Bhalme in 1976, they looked at several rainfall data time series over central India, then the monsoon trough, the pressure variations over monsoon trough, and the pressure over the Mascaran high, etc., etc. And they looked and they looked at their temporal behavior. They sort of looked at this power spectrum. What are the energy in different periods? And they found that there is power in about 10 to 20 in almost all these different variables. There is power in high power in 10 to 20 day period. So they identified that this must be a kind of a spatial phenomenon. So they started calling this as a sort of biweekly mode, and then they looked at something else. In order to try to understand what could have caused this possibly, they also looked at the time series of the moistatic stability over central India, and that also has a similar. This is the biweekly mode, I think, and this is the 30 to 60 day mode. So it also has a biweekly period. So they figured out that it must be related to the stability is sort of radiative convective process, and that temperature stability depends on the radiation and the convection, latent heat release and radiation interaction. So based on that, they proposed a hypothesis how these 10 to 20 the oscillations could have arisen. And according to their hypothesis, they said essentially, suppose there is no cloud and solar energy, solar radiation will try to heat up the surface temperature and surface temperatures will rise. When surface temperature become hot, the temperature profile in the atmosphere becomes unstable. So the lux rate becomes large, and the temperature profile becomes unstable. When temperature becomes unstable, so the convective instability will initiate convection, and the convection will then if there is enough moisture, which is there in the monsoon time, then the clouds will form, the convection will start, clouds will form, and the clouds will then produce, if there is more cloud, the solar radiation will be cut down, and it will of course produce the latent heat, which will heat up the upper atmosphere. Now it will cool down the lower atmosphere and heat up the upper atmosphere. So these two things will make against temperature profile. So if it goes on for some time, it will make temperature profile stable, because it will now cool down the lower atmosphere and heat up the upper atmosphere. So temperature lapse rate will decrease, and therefore the temperature profile will become stable. Then the clouds will become, then the convection cannot be sustained, clouds will dissipate, solar radiation will again try to heat up the surface and produce heating, surface heating, then temperature profile will ultimately become unstable, and again the process will start. So this is process, it's a plausible hypothesis. Unfortunately, they did not quantify it completely because they could not calculate those that it will give us this kind of periodicity. But then they also did, after when more circulation data was available, they looked at more about their spatial scale of these. Krishnamurti and another study, they showed that this is, by the way, in 1979, there was a 1979 is a global first Fiji observation experiment. That by early 70s, we recognized that we can make weather forecast using numerical weather prediction models, but we need good initial conditions. But there was very few observations around the globe which can give us good initial conditions for these models. Therefore, a very major effort was organized by the world community, the WMO, and the world community and a lot of countries joined for enhancing the observation over land as well as over the ocean by various different processes. Over this 1 year period, there is a lot more observations were made. And at the end of that, by aircraft, by ships, and by all kinds of kind of the regular observations were intensified and so on. So that particular year gave us a whole lot of real observations, and that was then analyzed by a weather prediction model. So you got a three-dimensional structure of the whole atmosphere with a lot of data going in, and that data set became a very useful source for studying a lot of things. And that data set was used in this study, and I'll refer to that in many other studies. And then they looked at surface pressure from that analysis during monsoon time or that 1979 period, and they filtered out the 10 to 20 day period of the surface pressure, and then looked at their time evolution and averaged over the 10 to 20 day, 10 to 20 degree north, 10 degrees to 20 degree north, if you do, and then look at with longitude and time, you see that different phases of this oscillation is propagating from east to west. The time goes this way, and the east is here and west is here. So there is a westward propagation, and they could actually estimate something the phase speed of these. So a new phenomenon. Now we know the time scale. There is an oscillation with time scale of about 10 to 20 days. We also know that it has a westward phase propagation. So now we are getting more and knowing more and more about this oscillation. So following that, Chen and Chen, they looked at the same data and looked at some more things and actually came up with. So this study still, it could give us a bit about the horizontal from the structure, the half wavelength we can estimate from here, and therefore we could get an idea about the wavelength. But still, we did not get a good idea about the circulation associated with this. So Chen and Chen actually looked at more details about the circulation and did a composite, created an index for this mode, and then do a composite structure of the wind anomalies associated with them. I'm not going to show great details of their work, but they are the first time they showed that associated with this oscillation, the wind anomalies have a very interesting twin cyclonic vortices around about 10 degrees north. So this gave us an additional information. Now we have a westward propagation is one characteristics. The twin vortices around are associated with generally equatorial Rossby waves. So it gave us also idea that maybe these 10 to 20 day oscillations are somehow related to the equatorial Rossby wave. But there is, of course, a problem of defining if it was dry equatorial Rossby wave, they should be centered around equator, but they are not. They tend to be centered around 10 degrees north. So that was another problem, but needed to be explained. So then Piali and I did. Piali was a master student with me some time back, and she did an outstanding work on looking at the structure, all the spatiotemporal structure of this oscillation, and also trying to understand what drives this. So first, she looked at created an index of these filtered winds, and then from that wind you can actually create a composite structure of the anomalies, and it turns out that the twin vortex structure comes out very clearly. And if you do a sort of lead lag composite for over the whole period, about 50 more than 15 days, then you see that there is, of course, a positive phase or the active phase, and there is a negative phase. The structure of the winds is just reverse. That is very interesting. But you can look at a sort of their phase propagation by doing the different phases. You can do an average the vorticity around around 10 degrees, and then you plot it with time and longitude, and you get this phase propagation very nicely. And from this phase propagation, you can estimate the phase speed. And from this size of the vortices, we can actually estimate the wavelength is about 6,000, between 6,000 and 7,000 kilometers, and the phase speed is about 4.5 meters per second. So now we have everything. We have wavelength, we have time period, we have the phase speed, and so. And they definitely look like a equatorial Rossby, but they're centered around 10 degrees. This is the one vortex that side, another vortex this side. Ideally, in a dry atmosphere, this should have been centered around equator, but it is not. And this is something that we needed to answer. And also we needed to show that how does this Rossby wave become strong, and where does it get the energy? So we proposed, and so so it can actually show that with the different phases, this westward propagation of these twin vortices can be seen very nicely. So all that can be seen. And even in the winter, if we look at it, we can see that even this happens even in the winter. But the vortices down there are located south of equator, around 5 degrees south of equator. So this, therefore, in summer and winter, the center of the vortices are slightly different, and they are located not exactly the same, 10 degrees north in the summer and the 5 degrees south in the winter. And both these things we need to explain actually. So then, in order to try to find a mechanism by why how they get energy, we looked at the relationship between the divergence at near the surface or within the boundary layer and the rainfall or the OLR. And it turns out that there is a strong correlation between the low-level moisture convergence or the moisture divergence and the rainfall associated with this mode. And therefore, it indicates that the boundary layer moisture plays an important role, and that moisture convergence is essentially related to the convection. The convective heating associated with boundary layer convergence is important in this. So for that, with this kind of a background, he created built a simple model, a two-layer model in which the atmosphere had 2 layers, and you express these winds and pressure at these 2 different, and the heating in the center of the center of this at the level in between, and vertical velocity is 0 at top and bottom. But there is a mixed layer to which the convergence will give rise to entrainment. This entrainment then produces the convection, and then you can parameterize the convection proportional to the rainfall. The rainfall is related to the moisture convergence, and the boundary layer moisture convergence is essentially related to the rainfall. And so you can parameterize the rainfall, and you can put this is a sort of set of linear equations. And then from this linear set of equations, you can try to find out what are the unstable modes. And from these unstable modes, we were able to figure out that there is at least one unstable mode, which is the maximally growing. And that maximally growing unstable mode had about 6,700 kilometer wavelength, phase speed about 4.8 meters per second, and period in the right about 16 days, right in the ballpark of what is observed. And they had obviously similar structure, similar to this. But then if there is no mean flow, therefore, so we had this model where we included mean flow, but we did the first study without the mean flow. When you do the Rossby waves are centered around the equator, but then when you include some realistic mean flow, I did not show that, but when you include the realistic mean flow, that mean flow actually makes it to move the center of the vortex to the north, because in the mean flow we have the cyclonic mean flow has a cyclonic vorticity to the north of the equator, and therefore the absolute vorticity 0 is north of the equator. Actually, it is around 10 degrees north, and that actually is 0 of the absolute vorticity. Not as when there is a mean flow at equator, if there is no mean flow, the equator there is absolute vorticity is 0, the Earth's vorticity is 0, absolute vorticity is 0. But when you have a mean flow, it is the absolute vorticity 0 is like a dynamic equator, and therefore the Rossby waves are around this dynamic equator, and that is where they are. So this is everything. In the summer also you can winter also you can explain, because mean flow is different, and you can explain that the absolute vorticity 0 was south of the equator, and you can actually show that the Rossby wave should also be located south of the equator. So this is a Rossby wave, equatorial Rossby wave, analyzed by convective feedback, which is essentially through boundary layer convergence of moisture, gives rise to the vorticity. So this kind of a cyclonic vorticity on the convergence gives rise to a cyclonic vorticity at the low level. The cyclonic vorticity will give rise to further entrainment into the on the boundary layer. Entrainment will give further enhance the heating. The heating enhancement of the heating will give rise to low pressure and further enhance the cyclonic vorticity, and cyclonic vorticity of this sort of wave will intensify through this process. So there is a physical mechanism by which this can happen in the presence of so this is essentially, as was shown by Chen and Chen, that this structure is indeed similar to Rossby waves, but it is essentially energized by and made unstable due to convective feedback. This quasi-biweekly oscillation is actually very important, and there is many different many phenomena which are seen. Even in the Indian Ocean, we see a very robust, very strong biweekly oscillation. This is near Sri Lanka. There used to be a few moored buoys, which some scientists had put them there, and the Scott and company actually analyzed these. And there are the mood buoys had current meter measurements. So therefore, the north-south velocities were recorded, and when they analyzed these, they found that the north-south transport, the meridional transport, had a very strong biweekly oscillation, and that at that point of time they did not realize, but later on we did, my colleague Sengupta and had looked at forced the ocean model, and with the observed winds which are associated with this biweekly oscillation. So the biweekly winds in the atmosphere can produce these oscillations in the equatorial ocean. In fact, the projection of these Rossby waves actually produce an oceanic mixed Rossby gravity wave, and that mixed Rossby gravity wave produces these biweekly oscillations in the ocean. So this have interesting applications in the ocean. So with that, I'll stop now for a few minutes to take questions, and then we'll go to discuss the 30 to 60 day mode oscillations, or what you call monsoon intra-seasonal oscillations. Okay. So next I'm going to discuss about this 30 to 60 day mode, or the monsoon intra-seasonal oscillation. This was another oscillation that was known for by Indian meteorologists for quite some time. Like early on, Dakshinamurti and Kesavamurti, by looking at some station data, they found that there are some oscillations in the period of about a month. So they recognize that, they recognize that they must be related to these active and break spells. But again, at that point of time, we did not know what is the spatial structure of these and what causes them. And this is just an example of wind averaged over this region. One is rainfall and the other one is winds. So if you take a time series of rainfall and wind, both have these oscillations around 30 to 60 day period. And that this is now, I mean, this is recent data that I have taken, but this was known by meteorologists for quite some time. But in those early days, we did not know the large scale nature of this. And that is what became clear when the satellite data started becoming available, and when this large scale global analysis became available. And that is, for the first time, I think these two studies who actually were crucial in sort of bringing out the large scale structure was one study by Yasunari in 79, where he looked at at that time, the satellite have started bringing in some visible pictures, and then sort of digitized data from the visible imageries. He plotted the cloudiness. It's a measure of cloudiness, and that cloudiness, if you average over 70 to 84 degrees east and plot with time, latitude and time this way, then you see that these cloudiness bands. So this is like the cloudiness has a band. So this is like a band. This band seems to move from south to north. So there is a northward propagation of this cloudiness band. And this cloudiness band then reaches north about central India. And then another one forms here, and then moves again to the north. So this repetition time is about a month or a little more than a month. So that is what was indicated, that this must have a large zonal scale, and it has a periodicity of about a month. And most importantly, first time, those station data did not tell us about it is northward propagation. But now, for the first time, we could see that they are associated with a very strong northward propagation. So this is something that, and they keeps repeating this northward propagation, and seems to be generated somewhere close to the equator, and then propagates to the north. And the same thing was seen in another study almost simultaneously by Sikka and Gadgil, and they also looked at visible pictures like cloud bands like these. They called it a maximum cloud zone, and then more than 10 degrees longitude average they took and looked at where the position of this cloudiness band day after day, and plotted the position as a function of time and latitude. So this position of this band also moves just like that. This study showed this position also moved northward with a period. And of course, in this from this, you can also get another thing. What is the northward phase speed? It's about 1 degree per day, something of that order. This is also a number that comes out from several studies, roughly, maybe a little bit this way or that way, but somewhere around that. And same thing, this study also found that, okay, they propagate, they seem to develop close to the equator, propagate northward at the speed of about 1 degree per day. And then, in other words, in about in about 30 days, they will reach 30 degrees latitude. So that is roughly, that is what. And then again another one forms here, and then propagates to the north. When it becomes very strong in the north, the equatorial one dies, and then after some time the equatorial one start developing, and then again it propagates. Then when it starts propagating, the north one dies. So this is the kind of picture that also can be seen here. So when it becomes strong, the equatorial one dies, and then when it gets established, and sometime later the equatorial one starts forming again, and then propagates. As it propagates, the north one dies at some point of time. It cannot sustain, and then it again reaches north latitude, and again, and then the equatorial one dies. So this brought out some additional interesting features about this oscillation. This is a northward propagation phase speed. It's a large zonal scale. So this large long cloud band indicates that this has to be related to the ITCZ, because this is essentially a ITCZ related, ITCZ dynamics. So in other words, the ITCZ we have seen that on a seasonal time scale, ITCZ goes from equator to about 30 degrees, 25 degrees, and monsoon gets established. And it stays there for the season. But then within the season, and these episodes takes place about 3 or 4 of them, such episodes takes place every season. So in other words, it looks like that the ITCZ itself has over the climatological seasonal progression. On the top of that, there are subseasonal fluctuations of the ITCZ, and that subseasonal fluctuation takes place at the time scale of this about a month and a little longer than a month, and they seem to be related to these two positions of the ITCZ. One is the favorable position over the land, and another favorable position over the ocean. Then when one is strong, the other one tends to be weaker, and when the other one becomes strong, the oceanic ones tend to be weaker, and vice versa. So this competition between these two ITCZ is an integral part of this oscillation. But as this, there is also inbuilt this the northward propagation on the top of that. So these two things are simultaneously happening, and that sort of coincides with the same time scale. So this was the scenario, of course, looked at on various other years and how it happened. There is year-to-year variation, but that's not so important. I mean, it is important, but let us not dwell on that too much right now. But once we realize that, okay, there is a spatial scale which is much larger. Now then, Indian meteorologists, of course, had a lot of rainfall data over the whole country. So we started looking at within the country, what is the spatial scale of this oscillation, and then how does it sort of propagate within that. So we used Rajiban et al. They used a lot of data from daily rainfall data, and and created composites of this active and break spells, sort of peak phases of these oscillations and the weak phases of the oscillations. And it shows that, and then did some lead lag composite of these. And so it during a break, you see there is negative anomaly over this whole central Indian region. And there is, when there is negative anomaly, there is positive anomaly in the eastern part. So there is, and this is all from rainfall data. So this is what I was telling you, telling just now, that when there is a break phase, the tendency of an active phase over the in the northeast and also over the southern tip of India. And then this break phase is sort of, if you see, there is some sort of a northward propagation of this weak negative anomalies tend to become organized and become strong and move northward, and then move further northward, and then sort of northeastward and dissipate. And then the positive anomaly starts coming from south. These positive anomaly starts propagating, sort of advancing towards north, and then after a few days, it will become an active phase over the central India. And then so if you do a composite with respect to active, you see more or less similar picture in the opposite sign. When there is active phase, there tends to be a break phase in the eastern India and over the southeast peninsula, and it has the same kind of northward propagation. So within the country, we have a similar figure that there is a northward propagation. It has a large scale, but still, because it is a land, we still don't get the full picture. Now, that full picture of how this happens can be obtained from satellite data. Now we have satellite data. Satellite data, satellite daily rainfall is available. Satellite OLR is available. So outgoing long wave radiation is available. So we can, from those, we can actually get the full picture over the, so how this oscillation is related over the whole region. So when we do similar thing, a kind of composite of these active and break spells using, this is called ZPCP. This is a rainfall product, the daily rainfall product, combining the in situ as well as the space-based observations. And based on that, we composited these lead lag composite of active phases of this the monsoon intra-seasonal oscillations. And this is the kind of, if you see at lag 0, this is a kind of break phase. So at lag 0, we have a break phase. There is a negative anomaly, and when this negative anomaly is not only over central India, and there is positive anomaly in the northeast and the southeast, but it is elongated in the northeast to southwest to southeast to northwest in the ITCZ kind of way. And so it has a much larger scale than just over the continent. But most interestingly, you can see that when there is active negative weak phase or break phase over our continent, there is an active condition going on over the equatorial Indian Ocean. So the positive anomaly. So this is a kind of meridional scale of this phenomenon. So there is a meridional scale. There is a zonal scale. Zonal scale is very large. It is the kind of ITCZ. So, and when it becomes an active about 15 days down the line, this break phase becomes active phase. Then also it becomes active over this whole ITCZ region. So this is associated with the ITCZ fluctuations, and it has a large zonal scale which encompasses the whole Asian monsoon region, and it has a large sort of meridional scale in which the continent and the ocean tends to go out of phase, and so these are kind of important characteristics of these oscillation. And when you look at the winds associated with these, one interesting thing, this is a composite of low-level winds. So associated with the active phase, the low level winds has this cross equatorial anomalies and the cyclonic vorticity. You remember the mean monsoon circulation. Mean monsoon circulation is like that. Only these are anomalies. These anomalies, of course, the scale is different. Mean monsoon, mean winds have a scale of about the maximums. The maximum will be about 10 meter per second here, or 12 meter per second. But here now I have a, the unit is just 2. So there are a couple of meters anomaly are produced, and that is actually enhancing the whole monsoon circulation in the active phase. And the break phase, it will simply be opposite. So these monsoon, these active and breaks, the subseasonal fluctuations change the whole monsoon, large scale monsoon, intensifies it in an active phase and weakens in the break phase. Accordingly, it also produces the less rainfall during break phase and more rainfall during the active phase. So this is how it is linked. So there is a possibility, because of the very large scale, they can influence the large scale monsoon significantly. And this is this particular, these are again two composites of these active and break phases by using the same GPCP data. But here I have composited not only the winds at 850 millibar, or here I have composited the meridional, the overturning circulation associated with this. So if I do a sort of average between 75 and 85 degrees east, and over the vertical direct height and latitude plot, if I make, in the active phase, there is ascending motion in the around 25. That is where the monsoon is active. The monsoon gets enhanced. The vertical velocity also gets enhanced over the monsoon region, and then there is a descending motion around equator or around 5 degrees. Remember that the mean circulation, mean and the monsoon headly circulation has descending motion further to the south, around 20 degrees south. At this position where there is a rain band in this, there is actually an ascending motion in this region in the mean. But now in the subseasonal time scale, it produces descending motion over that ITCZ, where there is to be a secondary rain maximum. And so the meridional scale of the subseasonal fluctuation is smaller compared to the meridional overturning circulation in the mean headly monsoon headly circulation. But however, it can still interact with the mean because of this enhancement and weakening of the mean circulation over the land. And so that is, and it is of course convectively coupled, because if you do what produces this oscillation? To understand that, we looked at what is this relationship between the rainfall and the winds, for example, circulation. So what you do, what is plotted here is a space-time spectra, just like that Wheeler and Killardis paper that I mentioned, where you can do a space-time spectra of both rainfall and the winds. And if you do space-time spectra of rainfall over the monsoon region, you get maximum in this time scale, 30 to 60 day time scale, and wave number about wave number 1, between wave number 1 and 2. So, and if you do the winds, also you get exactly same time scale and wavelength, and therefore these two, the winds and this the precipitation are seems to be strongly coupled. It of course does not guarantee that. These are just you have to see the coherence, and it turns out that the coherence between these oscillations of the winds and these and the rainfall are also strong. By with this knowledge, you can actually develop some sort of a monitoring index of these, just like the MZO index, how people monitor in the real time. We developed a real-time monitoring index of the monsoon intra-seasonal oscillation in the form of if you do some sort, if you do a sort of extended empirical orthogonal function analysis of the rainfall, you can find out two UFs which sort of represent this oscillation, and using those as two indices, this represents the oscillating character of these indices, and depending on the amplitude, it indicates that when it is strong, and when these two in the phase space of these two indices, it indicates different phases of these oscillations, where the convection will be, and whether the convection will be strong and weak, and whether it will be positive or negative phases. It can be obtained from this phase space diagram of these two indices, and that is very useful, and people are beginning to use that for some analysis as well as monitoring of these. So why these oscillations are important? Because the amplitude of these is quite strong. If you look at the variance of the subseasonal oscillation or the intra-seasonal oscillation, including both QBM and the MISO, if I take the filtered data of rainfall between 10 and 90 days and do the variance, this is the standard deviation of the GPCP rainfall at 10 to 90 day filtered rainfall, and these units are as large as the standard deviation is like 11 to 12 millimeter per day, which is as large as the annual cycle of mean. That means the amplitude of these fluctuations are as large as the annual cycle. This is very large. On the other hand, if we look at the interannual variation of the seasonal mean, which is about 3 to 4 times smaller. So if you look at the seasonal mean, June to September rainfall, and look at their year-to-year variations, and you'll find out the standard deviation. And this is represented here, which is much smaller. So the year-to-year variation of the seasonal mean is much smaller, but within the day-to-day fluctuation, within the amplitude of the day-to-day fluctuations associated with the intra-seasonal oscillations is much larger. Therefore, they are kind of a non-linear, and therefore they can have some influence, residual influence on the seasonal mean, and that is why they become quite important. They also modulate our the synaptic activity. So we showed for the first time that you looked at a lot of data. We looked at over many years, and looked at and identified the initiation and the movement of these low pressure and depressions during an active phase of the monsoon intra-seasonal oscillation, and during a break phase. So under all break phases, if you see how many of these oscillations, these low pressure systems. Low pressure system means lows and depressions, and maybe even tropical cyclones. So if you include all of that and look at their statistics, it turns out that during an active phase, most of the number of occurrence or the frequency of occurrence of these low pressure systems are about 4 times larger than the number that occurs during a break phase. And also during active phase, they tend to be concentrated around the monsoon trough region and then propagate westward. During break phase, some of them simply happen to move and get locked with the Himalayan region, and some of them happen closer to the ocean and they propagate westward, and they therefore do not affect the continent. So they don't contribute to our sort of land rainfall. So it clearly sort of modulated the frequency of occurrence of these monsoon synaptic activity by this. So thereby Therefore, during this time active phase, they contribute a lot to the rainfall over the monsoon region, over the continent. On the other hand, during break phase, the synaptic disturbances do not contribute so much to the mean rainfall. So what produces the oscillation? So the one question is still there, that okay, there is a 30 to 60 day oscillation, but what drives this? Why 30 to 60 days? So this was the open question for quite some time, and then sometime way back in 84, we did a bit of modeling study. I used this this generally symmetric general circulation model at the Goddard Space Flight Center, the Goddard Laboratory for Atmospheric Studies. They had this model, which I made it to a symmetric model, which is representing the ITCZ. So from the three-dimensional model, sort of, I developed a two-dimensional model. So the X dependence was removed, and therefore using that we could study the ITCZ basically. But it had all the physics in it, like how the clouds are produced, and how clouds produce give rise to heating in the atmosphere, and that heating then affects the heat budget. That heat budget will then affect the circulation. So there is a circulation and convection feedback which was built in. Now we simulated this with this model. We simulated a relatively long RAM. At that time, the computers were also not very big. Even at NASA, the computers were limited, and I could only run for about 100 days this GCM, and the simulations indicated that this is the result of those simulations which produce rainfall here. And these are stream functions, generally symmetric stream functions at 500 millibar and 200 millibar, I think. So what it shows that the stream function represents the Hadley circulation. So the ITCZ essentially. So the ITCZ has a fluctuation of a period of about 1 month. So does the rainfall. Rainfall also has a fluctuation of a period of about 1 month, and they tend to happen and initiate about near the equator, and tend to seem to propagate to the north, and somewhat similar to what is observed. Of course, it is still a limited simulation, but it was very clear that the interaction between this convection and dynamics produces a oscillation of the Hadley circulation, Hadley circulation or the ITCZ, and the oscillation has a period of roughly about a month. And that was intriguing, because that is what we actually didn't really predict that before we got the results. But then when we went to the next stage of trying to understand that it's essentially due to this feedback between the convection and dynamics. So what you can do, you can experiment by switching off this interaction. So you switch off the interaction. Instead, how do you switch off the interaction? So you can do, instead of letting the heating being modified by these clouds will produce the heating, but in the forcing, you don't allow that heating to go, but you prescribe the heating, fixed heating from the clouds. So if the clouds heating is fixed, then of course radiation budget will continue to produce whatever that is, but the heating coming from rain is fixed, and if that is fixed, then the model, the ITCZ, does not fluctuate at all. So that gave us the confidence that this oscillation is essentially due to the feedback between a convective radiative feedback, a convective radiative dynamic feedback process. So essentially, it is something very similar to what Krishnamurti and Bhalme proposed for 10 to 20 days, which actually it was, unfortunately, that was not correct. But but it happens on 10 to 30 to 60 daytime scale. So essentially, the net radiative effect warms up. We looked at sort of these budgets and all that, and so it confirms this kind of feedback that is happening. Net radiative effect warms up the surface, making surface temperature profile unstable, builds up dry and moist instability. So latent heat of convection heats up atmosphere. CISC, that heating up atmosphere, produces low pressure area, and it further intensifies the ITCZ. This is a kind of CISC, that the conditional instability of second kind sets in, and that sets the conditional instability of second kind intensifies the ITCZ. But it is a kind of unstable situation, but it should continue indefinitely, but it cannot continue indefinitely because it will go on intensifying. But when it intensifies, it produces a lot of cloudiness. When the cloudiness becomes too much, it essentially cuts down solar radiation and produces a negative feedback. It cuts down solar radiation and therefore cools the surface and warms the upper atmosphere. Therefore, it stabilizes the atmosphere. It also brings in the upper atmosphere a dry air convergence, and therefore sort of reduces the moisture in the upper atmosphere. All this produces a negative feedback, therefore cuts down the instability and stabilizes the atmosphere. Once the atmosphere becomes stable, convection dies down. And when convection dies down, then the clear sky comes up. And once clear sky comes up, again the surface becomes, and it takes certain amount of time in doing that. When it and then after a certain amount of time, when the clear sky continues, the atmosphere surface become unstable. Again the instability starts, and then again the CISC can produce intensification of the ITCZ, and it will go on for some time until it can again cool down the surface and cut itself up. So this is a process by which it can actually intensify and produce the oscillation as well. So that mechanism seems to be quite robust, and but it was supported by later on several theoretical studies were using linear models or simpler models, which we could understand much better than a GCM. GCM has a lot of different feedback loops. So essentially that is the core mechanism through by which the scale selection and intensification are explained. Of course, recently there is some more studies which essentially are going looking at it in a slightly different way. Instead of this feedback, this is also feedback, but instead of this kind of a feedback that I mentioned, you can think like these are some normal modes of the moist atmosphere, tropical atmosphere. These are called moisture modes. The Madden-Julian oscillation as well as boreal summer intra-seasonal oscillation, like our MISO, are now being considered as moist modes, moisture modes. In other words, moisture modes means these are intrinsic normal modes, just like our, as you remember when I discussed the equatorial waves and I showed the Wheeler-Kelladis the diagram. There the MGO comes in, which has no correspondence in the dry atmosphere. Dry atmosphere, there is no normal mode like that. So MGO is essentially it comes in only a moist atmosphere. So, but that theory, there is no theory. And now you have a theory which can tell us that there are certain moisture modes. If you have moisture, you can sort of develop normal modes, including moisture and its feedback into the system. So these are kind of MISO as well as MGO could be now understood in terms of moisture modes of the tropical atmosphere, and that is also a new understanding that is emerging. So they are not independent completely, but it is a better way of closer kind of thing. So these are important developments that are taking place in understanding. Now, other question that remains is, okay, So that is the scale selection. So why 30 to 60 day mode? What gives this energy? So the energy comes from the convective feedback, convective radiative feedback, and the instability, and that kind of CISC kind of process that goes on inside. The other thing is has to be explained is northward propagation. What produces northward propagation? And I mentioned this briefly in discussing ITCZ, but here in the context of the monsoon intra-seasonal oscillation, we recognize that that when you do these composites, of the precipitation or the OLR and the winds and vorticity. Suppose I take the vorticity and do the composite lead lag composite at zero lag. We have. Let me see what is this. This is negative. So this is a break condition, and these the lines. The shaded region is OLR, and shade is OLR, and the contours are vorticity. So there is a break condition, rainfall, and so there is this is the vorticity. Now, if you see the vortex center and is slightly north of all these the OLR pattern. So everywhere here also, this is a kind of 20 days. This is cyclonic vorticity. So negative OLR means actually active condition. I'm sorry. So negative OLR means active condition. Active condition is associated with cyclonic vorticity, and the cyclonic vorticity is just north of these the OLR centers. So and in the break conditions, you have anticyclonic vorticity, and that is also north of these OLR center, which means that there seems to be that the vorticity anomalies are slightly north of. This is just above the boundary layer. It's about 850 millibar. And these vorticity anomalies seem to be slightly north of this. And based on this observation, and this can be seen from the lead lag time series, and you see that this is latitude, and time goes this way. So at any given time, the vorticity center is not of the OLR center, and that is something that we noticed. And based on this, a theory has been now has been developed by Jiang et al. And this is a very quite interesting theory, and they have gone into sort of theoretical framework of how an ITCZ kind of zonally average in the zonally averaged ITCZ precipitation in a zonally average ITCZ can produce circulation anomaly, and how circulation anomaly can give rise to changes in the convergence and divergence of in the boundary layer, and that convergence and divergence of the boundary layer, how can it change the location of the ITCZ or the heating. The ITCZ represents a region of heating. Because initially there will be a lot of rain over there, right? So that heating is essentially produces a first baroclinic mode heating. That first baroclinic mode heating can give rise to anomalous circulation anomalies, and that circulation anomaly response can give rise to anomalous convergence of moisture in the atmosphere, in the lower atmosphere, and that anomalous convergence of moisture can give rise to can contribute to this northward propagation. The way it does depend on two things. One, if there is a northward gradient of increasing northward gradient of mean moisture at the low level, then this heating in the beginning, the upward motion in the ITCZ and the heating can give rise to the moisture convergence in the boundary layer slightly north of this region, the anomalous moisture convergence becomes slightly north of the original heating, and therefore the moisture convergence in the heating itself goes to the northern to the north of the original heating, and therefore the ITCZ itself will move to the new location of the heating. And that is one possibility. The other possibility also happens is in the presence of an easterly shear, the mean flow. Mean flow is easterly during this time, and such an easterly flow again will the atmosphere not in the the first part is essentially due to the boundary layer dynamics. If you force the convergence at the top of the boundary layer dynamics, including the Ekman processes, will produce this anomalous convergence to the north in the presence of the mean humidity itself has a gradient. If the mean humidity itself has a gradient, positive to the north. If that happens, then the convergence in the boundary layer convergence can be north of the original convergence at the free atmosphere, and that will then make the heat source move to the north. On the other hand, a similar thing can happen from the atmospheric dynamics itself, not just the boundary layer dynamics. The heating itself can produce atmospheric circulation in the atmosphere, and that the heating, the first baroclinic mode heating can give rise to, in the presence of an easterly shear, can give rise to a barotropic vorticity, a cyclonic vorticity response to the north of this. This is anomalous vorticity response. The anomalous vorticity response has a barotropic component, and that barotropic component is maximum to the north of this. And if there is a cyclonic vorticity which is forcing the boundary layer at this location, this will produce a boundary layer convergence due to the Ekman processes in the boundary layer, and that boundary layer convergence will then produce more moisture convergence in this region and produce more heating, and therefore the heat source itself will move to the north. So there are two potential mechanisms by which the ITCZ itself can, due to its own response or the forcing of the atmosphere, it will produce anomalous response in such a way that the convergence of moisture is going to be north of its equator, and that convergence of moisture is going to lead to a heat source which is going to be stronger to the north of the equator, and then therefore the original heat source will move to the north, and thereby, and once that gets established, that will then produce response in the atmosphere, and after a few days that response will produce the movement to the north, and so on and so forth. So that way there is a possibility that these the feedback mechanism itself can make the ITCZ move to the north, and therefore the northward propagation can be explained in terms of this atmospheric response of the ITCZ heating itself. So there is a framework that through which there are also some debates and some details are people may not agree, but I believe that this is a pretty reasonable framework to understand these. So another question that we asked is what kind of, how far ahead these we can produce sort of, what is the potential predictability of these ISOs or these active break conditions? That question was not known, so some people did. This question can be addressed two different ways. One you can do is do some predictability experiments with a model. You can perturb the initial conditions and make predictions of these ISOs, and then see how the errors grow, and when the errors becomes as large as the signal, and then you can say that okay, beyond that we cannot predict. That is normally that is the thing that is done, and people have done that also, and that also shows that the potential predictability of the maximum may be we can predict it is about 20 to 25 days in ahead. Now, what we did is looked at it from the observation itself. From the observations itself, can we make an estimate of what is the potential predictability? How do you do that? That can be done. Suppose I have an index of this ISO in some way. Forget about what is this index. Now, this index essentially represents that. So these are the events. So these this normalized index. So the normalized index rather than 1 represents these active events, and there are some break events. So now suppose these active events, these all of them oscillates. So the active event goes to a break event, then fluctuates, and then comes to an active event, then again it goes to a break event, an active event, and so on and so forth. But the oscillation is not very absolutely regular, and there are differences in the amplitude. Suppose this is the amplitude of these, all the active events are quite different. One is different from the other. Now what we can say is that our predictability will depend on how the evolution of the cycle depends on the initial condition. Now one thing we can say that this initial condition, suppose I consider these as the initial state and the active conditions, and the different events have different initial state. Now they have evolved to have active break condition. What is the difference in their evolution? If the difference in their evolutions will be dependent on difference in the initial states. So if I can do a sort of, I can find the difference in the evolutions or the divergence of the evolutions from the active state to the break state, and from break state to the active state, how do they evolve and diverge? If I can quantify that, I should be able to estimate what is the divergence of evolution. If the divergence of evolution will give me an estimate of the growth of error in the natural system itself. Of course, we have no control on this initial perturbation. Initial states are different, significantly different. In fact, that means the initial differences are quite large. It is not a small perturbation. But even then, we may be able to get some idea, and that is what we did. So what we did is that we take all these different. Maybe we have many such events, right? 60, 70 oscillations, and then each oscillation, if I take from initial, this is a break condition. I'm sorry. Break condition is blue. These are break conditions, and this is active condition. So these break conditions, each of these are one break, and this one break then evolved to the next active condition. So negative side is the active condition, positive side is the break condition, and these are the active conditions. Now all these active then evolves to a break. And now if I can find out it, now one thing that I see is that all the breaks have a much larger diversity. I'm sorry. Active to break is blue. Active, this is active condition, and this is active to break is blue. So this is a positive anomaly. The rainfall we have taken, and so positive anomaly, active conditions are blue. Active to break is blue, and break to active is red. So this goes to an break condition. This goes to break to active. This goes to an active condition. So an active condition has a much larger diversity in the initial state. The break conditions have a much lesser diversity in the initial state. So there is a standard deviation. I can say that this is the initial error. Standard deviation of this. That standard deviation then diverges and becomes very large here, and that is the growth of error. The standard deviation, how the standard deviation from here to here grows, is the growth of errors. So this is what is summarized here. So this is the so when you go from active to active to break, it starts with a large initial error, but then it decreases. Then it remains, the growth rate remains low, and therefore it allows me to predict up to about 20 days ahead of time. But on the other hand, if I start with a break condition, the initial error is less, but then it grows very fast, and it reaches this is the amplitude of the signal, the amplitude of the oscillation itself, and that gives me a level. It reaches that level of the oscillation within about 10 days. So the break to active, the active conditions are much less predictable. That means if I start from break condition, and when I go to active, they are less predictable. Why? That is because as I go from break to active, you start the active convection starts to get organized, and active, you're going to active phase of convection. When you are going from break to active to break, your convection have started dying, and that is why errors have decreased. And that in the dying stage of convection, the convection is what it changes very rapidly, and that gives you error. And that in the dying phase of convection, you have longer predictability, while in the active growing phase of convection, you have less predictability. That is why active conditions are difficult to predict compared to the break conditions. So this is something, that understanding that we have evolved, which is I think accepted in general, and this is something that we see operationally as well. Okay, so I think I'll stop right in a couple of minutes. So we have also shown that these subseasonal or the intra-seasonal oscillations can actually contribute significantly to the seasonal mean. In fact, there was a study by Lawrence and Webster some time back. They showed that the variance of the ISO filtered OLR anomaly during for this period correlate positively with anomaly of seasonal mean rainfall. So this is OLR. Remember, the OLR is kind of opposite to the rainfall. So the inverse relationship was sort of the variance. Variance is the kind of amplitude of these oscillations correlate with the seasonal mean. So this was interesting. It indicates that these oscillations, the vigor of these oscillations, can influence the seasonal mean. And recently we have looked at them from also the variance of the synaptic disturbances 2 to 5 days, and 10 to 20 day oscillation, as well as 20 to 60 day or 30 to 60 day oscillations. If I correlate them with the seasonal mean, it turns out that the synaptic disturbance variance correlates very strongly and contributes significantly. So does the QBM as well as MISO, but they contribute negatively to the monsoon mean. And this is something that is emerging. So, and this is an area where active research is going on, and we still don't understand. We are beginning to understand maybe how these synaptic disturbances affect the mean, but how these variance or the vigor of these oscillations affect the seasonal mean is an area where we still don't understand very well. For example, I think it is reasonably easy to understand how the synaptic variance can influence the mean, because suppose you start with an external forcing like La Nina, and which starts a stronger delta TT, trying to strengthen the monsoon circulation. Okay, but monsoon starts with a stronger low-level cyclonic vorticity, and At low level, cyclonic vorticity will produce north-south horizontal zonal wind shear. Horizontal zonal wind shear produces barotropic instability. Barotropic instability is this synaptic disturbances essentially are fed by barotropic instability, and therefore stronger barotropic shear produces more frequent and stronger lows and depressions, and they produce more rain. Now, more rain will produce add to the delta TT to the north, TT to the north, and therefore strengthen the delta TT. Strengthening delta TT will produce strengthened circulation, and therefore again strengthen the monsoon circulation. So monsoon circulation will become strengthened. That will produce again strengthen the low level cyclonic vorticity, and therefore it will produce a positive feedback. And that is why there is a positive, seems to be a positive relationship between the vigor of the synaptic disturbances and these. But the same thing is not quite clear as far as the relationship between the seasonal mean and the MISO and QVM. I think there is still work to be done. With that, I will stop